The next couple of weeks, we're going to be talking about exponential functions and logarithms. Logarithms we'll get to later, so we're not going to worry about that for right now. But this week, we're going to be looking at these things as functions, and an important idea to really understand what's going on there is to first understand what we're talking about when we talk about exponential growth or exponential decay. Um, these are words that sometimes get kind of thrown around in like I don't know, just sort of a common usage sense to mean like something that happens fast, right? Like you might see I don't know, a news article that says something happened exponentially or something grew exponentially. And they do grow fast. That's not always taken literally, but the idea is basically that exponential growth or decay, and growth just means increasing, decay means decreasing. So in some sense, decay is just growth, but in a negative direction. It's like a y-axis reflection, flipped the other way. Just means growth or decay. So change, in short. That can be thought of in terms of multiplication. So in the same sense that when you look at a linear function, one way to think about it is repeated addition, and that's why the slope thing works the way it does. If you have a line like that, then to get from one point to the next, you can go up 2 and over 1. Right? And up 2 and over 1, what you're doing really is just adding 2 over and over again. Exponentials are kind of like that, but instead of adding, we multiply, but with a fixed base. So in other words, constant base, which we'll typically call b. So b is some numeric value that we're basically multiplying by over and over again. So I have a couple examples of what this looks like and how this works. And the first, we just ever so narrowly missed spooky season in this landing perfectly, but unless I reuse these videos in the spring, which I probably will. Okay, whatever. Um, and that's in modeling something like a zombie outbreak. So let's say that at the beginning of this whole thing, there's one zombie. So we'll start counting on day 0 just to make some stuff kind of line up later. But the beginning of this zombie outbreak, there's one zombie, and let's say each day every zombie infects one more person. That would mean that on the next day, there was one zombie, but that zombie goes out and infects another person, which means we multiply by 2 and get 2. The next day, now there are 2 at the beginning of the day, but if they each go out and infect another person, we're again multiplying by 2, so we get 4. So what's happening is that the number of zombies is doubling. 3, so we start with 4, that doubles to give 8. 4, we start with 8, that doubles to give 16, and so on. And what we see is all these powers of 2 showing up because what's happening is that we're doubling. So the number of zombies doubles each day. Which gives values like this, which we can think of as 2 to the first and 2 squared and 2 cubed and 2 to the fourth and so on. This is exponential growth with base 2. So again, that's kind of governed by this, right? The growth rate here is in this description that, if we're assuming that, like, I don't know, I guess once a zombie, always a zombie, like the zombies aren't dying or anything. But each day they go out and infect, just one additional person. So obviously we're simplifying things a little bit if you, know your zombie movies, but we go from 1 to, 1 additional, that's 2. And then 2, well, you got these 2, they each go find a new friend, and then we have 4, right? And then again, doubling over and over again. So the base is 2 because the way I proceed from one step to the next is this multiplication by 2. Now what that looks like, and we're going to spend, some more time with the graphs, but what that looks like is something like this, right? I've got this table, and okay, that's not what that was supposed to do. 2, and this worked before y'all got here. There you go, something like that, right? So these values are again doubling from one step to. I wish that worked. Oh well. And you can see like that they do grow, quite quickly. We started with a single zombie 10 days, and we're at 1,024, and again it's going to continue doubling. So if I zoom out a little bit, you can see this gets very steep very quickly. That's pretty characteristic of what exponential functions look like. So this is 2 to the x, changing the base just changes the growth rate and sort of how quickly it grows. We'll get into that some more in class. But that's the idea. The thing that makes it exponential, again, is that the way I get from one step to the next is by multiplying by a fixed amount. Okay, so that's an example of exponential growth. Now for an example of decay, stash this thing over here, I had to draw this. For an example of exponential decay, think about something like a single elimination tournament. So something like the NCAA basketball tournament is a good example. Anything where you play a single game and it's basically win or go home. So things like I don't know, the World Series don't quite fit because you're playing a best of 7 series, something like that. We kind of need this to be a single elimination, single matchup thing. So here I've drawn a bracket for an 8-team tournament, right? 1, 2, 3, 4, 5, 6, 7, 8 separate teams or participants or whatever. And if you're matched up in a bracket like this, that means that you're going to compete head to head. And whoever wins this matchup is going to get to advance to the next round. So there are 1, 2, 3, 4 first round like games that need to happen, consisting of 1, 2, 3, 4, 5, 6, 7, 8 participants, whether that's teams or individuals or whatever. Now, since each of those, one team is going to win and the other team is going to lose, the winning team advances. Right, so let me just kind of fill that in. I'll just mark with like check marks, right? So win, lose, win, lose, win, lose, win, lose, something like that. Then there are 1, 2, 3, 4 in the next round. These teams play, these teams play. Again, winner advances, loser goes home. So let's say this team wins and this team loses, and so on. Win, win. Okay, so now there are 2 teams remaining. They play, and we're down to 1 champion, right? So the number of teams then goes from 8 to 4 to 2 to 1. And, I don't mean to go too far into the sports thing, but, if you're a sports fan, you've are probably familiar with the NCAA basketball tournament, where you do this but on a bigger scale and go from 64 to 32 to 16 to 8 to 4 to 2 to 1, right? So it's the same idea, but just a larger scale of the thing. Well, the way I can think of this as an exponential decay situation is that to get from 8 to 4, I divide by 2, or in other words, multiply by a half. And again, here, multiply by a half. Here, multiply by a half. The only thing that changes here is that instead of the base being 2, the base is a half. And just throw that back on there so you can sort of see them both at the same time. Notice that these are symmetric, right? That's 2 to the x in black there, the one that's off now and then on again. So that's like the zombie growth rate thing we were looking at. And 1/2 to the x, like the number of teams left in the tournament, looks identical, except it's reflected across the y-axis. This makes sense if we think about it. If we think about exponent properties, two raised to the negative x would be the same thing as 1 over 2 to the x, or 1/2 raised to the x. Again, we'll get into that a little more in class, but it makes sense then that this is just 2 to the x with a y-axis reflection, because that's exactly what a negative sign there on the inside in the argument of the function would do, is a y-axis reflection. So, short version of the story. I don't know why I keep doing that, sorry. Short version of the story. Exponential growth functions look like this. Exponential decay functions look like that, because, again, one way to think about them is just as y-axis reflections of each other. Okay, so that's the basic idea. In class, we'll get more into the details of graphing and finding all of the usual stuff. You kind of know what it looks like now. And again, with the base being 2, stop doing that. With the base being 2, it means the points that you're going to, like the points that have nice coordinates along the way here, are going to be those that are powers of 2, right? So 1, 2, 2, 4, all the stuff I had written out in that table for number of zombies, 3, 8. So a convenient way that you can sort of sketch something like that by hand is to go, okay, well, 0, 1, 1, 2, 2, 4, right? We're going to pass through powers of whatever the base is. The next place that you would see like a nice integer valued point would be 3, 8, and so on. So probably a good exercise. I mean, we'll start class with this, but probably a good exercise to try to work through the graph of that a little bit, to get a feel for how these things work. Okay, and then later in the week we'll develop this idea some more, and then we'll introduce the idea of a logarithm and see how those work. Okay, that's it. Thank you for your time, and I will see you all in class.